Bismillahirrahmanirrahim. As in your last online lecture, we discussed about the introduction of Doppler effect, but in your yesterday class, we discussed about different terms related to transverse stationary waves in a string. So first we learned this topic, and after that we discussed the several cases associated with the Doppler effect. In this lecture we are going to discuss about the transverse stationary waves, because in last lecture we discussed about the several terms related with this topic. So first we learned this topic, and after that we learned about the different cases related to Doppler effect. So first of all, we define that what are transverse stationary waves. A standing wave obtained by the superposition of the transverse pulse is called transverse stationary waves. In last lecture, we discussed about the standing or stationary waves. That these are the waves which do not transfer energy from one place to another place, and these waves are found by reflection of the waves by certain spot. Like when you generate a waves in string, and after reflection from certain boundary, these waves superpose one another, and as a result there is formation of stationary waves. And stationary waves are those waves which do not transfer energy from one place to another. You discuss all these terms like superposition, reflection, standing waves or stationary waves, and the conditions for formation of the stationary or standing waves in last lecture. So in this lecture we are going to discuss about the transverse stationary waves in a string. For formation of transverse stationary waves inside string, let us consider a string which is clamped between two fixed ends. Clamped means it's fixed at two sides. We fixed it with certain support. We take a clamped spring which is fixed at 2 points A and B. This string having length L and mass M. When we clamped it between two fixed points, then there is tension in the string denoted by capital T. We take a string of length L and mass M, and we clamped it between two fixed points such that it's having tension T. Now when we plug that string at the center, then there is formation of two pulses which moves to opposite sides. One move towards point B and one move towards पॉइंट ए. यहाँ पे इसको हम दरमियान में जब प्लग करते हैं, ऊपर खींचते हैं, तो यहाँ पे आपके पास दो पल्सेस जनरेट होती हैं. एक पल्स मूव करती है टुवर्ड्स पॉइंट ए एंड अनदर पल्स मूव टुवर्ड्स पॉइंट बी. वन टुवर्ड्स ए एंड अदर पॉइंट बी. Here let's we plug that string at central point. Then there is formation of two crust. One crust move towards point B, other crust move towards point A. Then this crust or this pulse move with velocity v, and after reflection from point B, there is change of phase, means now this crust become trough. We discussed in last lecture that why there is change of phase at the fixed point, and this crust also move towards point A with certain speed v, and when reach the point A, now this crust also changes in trough. Now these two troughs or these two pulses after transformation, means after change of phase, they move towards one another and they meet at the central point. पहले आपने यहाँ इसको प्लग किया, आपने दो पल्स जनरेट की, वो आपने क्रस्ट जनरेट किया, ट्रफ जनरेट किया, जो भी एक टुवर्ड्स पॉइंट ए मूव किया, दूसरे ने टुवर्ड्स पॉइंट बी मूव किया. अब आप पॉइंट बी और ए और बी पॉइंट दोनों पे स्ट्राइक करने के बाद इनका फेस चेंज आया. लेट्स आपने यहाँ से क्रस्ट जनरेट करके साइड सेंड किया था जिसने वेलोसिटी वी के साथ मूव किया था. क्लम्प्ड एंड पे वो आपके पास ट्रफ में कन्वर्ट हो गया. अब इस साइड पे भी यही होगा. फेस चेंज के बाद आपके पास जो these two pulses move towards one move towards one side, other move towards other side, and while reaching the clamped end, there is change of phase, and now these two pulses move towards one another and they meet at the central point. Meet we mean that there is superposition of these two pulses at the central point. Now when these two waves superpose at the central point, then there is formation of a standing wave. Mean now this whole string vibrate in one loop. And you know that these two fixed points you call node, denoted by capital N, and the central point means the point where the particle oscillate with maximum amplitude. That point you call the antinode, denoted by A. Clear? Last lecture we discussed about these points, that these are called the nodes, and the points where particles of the medium means here the particle of the string vibrate with maximum amplitude. Now that point we call the antinode. And we also discussed in last lecture that the distance between two consecutive nodes or distance between two consecutive antinodes is lambda by 2, and distance between one consecutive antinode and node it's lambda by 4. Now this string length is L and it's vibrate in a single loop, mean at two sides there is formation of nodes, and we know that the distance between these two nodes is equal to lambda by 2. Here we discuss the first case in which we plug that string at the center, so we denote this wavelength lambda 1. So we can write the length of the string L is equal to lambda 1 divided by 2, because there is just formation of one loop and there is two nodes at this clamped end, and there is a antinode at the central point. So distance between two nodes is equal to lambda by 2. Here we discuss first case, so we write lambda 1 divided by 2, that's equal to the length of the string. If we want to find the wavelength, then from this expression we can write lambda 1 is equal to 2L. Here we consider that initially when we generate these two pulses, they move with speed v towards two fixed end, towards two clamped end. So by relation v is equal to f lambda, we can write the equation for speed. Here we take f1 and lambda 1 for first case. This frequency f1 and lambda is the wavelength for first case when we clump that string at the central point. If we write the expression for frequency, then from this equation, call it 1, then from this equation we can write f1 is equal to v divided by lambda 1. Here we have the value of lambda 1, that is equal to 2L. So this frequency become v divided by 2 times L. This is the first frequency we generate inside a clamped string. Here we generate the transverse waves inside a stretched string. That string having length L, tension T, and mass of that string is M. And in previous lecture we discussed about that the speed of the transverse waves depends upon the tension, length, and mass, and we write the expression for speed that v is equal to under root T L divided by M. Here T is tension in the string, L is the length of the string, and M is the mass of string. We can also write this expression as v is equal to under root T divided by M divided by L. We write this L on third place, and this is mass, this is the length. Mass per unit length is denoted by small m. Small m is the mass per unit length of the string. So we can write this expression for speed that v is equal to T divided by M. This is the expression for the speed of the transverse wave. So we replace this v with this value. We have expression for frequency that f1 is equal to, instead of we can write this value T by M. T by M under the root, this is the value of the speed for this is the expression for speed of transverse wave divided by 2L. Or we can write this relation as F1 is equal to 1 divided by 2L under root T by M. This is the expression for first frequency. That the frequency of the transverse wave in stretched string is equal to 1 by 2L under root T by M. L is the length of the string, T is the tension in the string, and M is the mass per unit length of the string. This first frequency we call the fundamental frequency or first harmonic frequency, which we get by stretching that string at the central point, and we just generate two pulses which move towards two opposite sides of the fixed end, and after reflection from fixed point they reflect back and they meet at the central point, and that whole loop vibrate, this whole string vibrate in a single loop. We derive the expression for the wavelength of that waves, that stationary wave, as well as we derive the expression for frequency of that stationary wave, and that frequency we call the fundamental frequency, or we call that frequency first harmonic. Now we plug that string in different points and we find the expression for wavelength as well as we find the expression for frequency while plugging that string at different points rather than the central point.